let's finish off. Two more talks. This is a pretty scary photo behind us. Pleasure to welcome and introduce a man that needs no introduction, but Prof. Hunter is going to a bit of an overview about the cardiac physiome in terms of where it might be going.
This is intended to be a, I think I am now. This is intended to be a very lightweight view of maybe some of the challenges for the next few years. I think the serious science has finished for the meeting, but I thought it would be worth just writing down what I thought were 10 points that we need to think about in relation to the next 3 years. I mean, it doesn't seem to me to be much point in going beyond 3 years and trying to anticipate what we might accomplish. And that's especially true from me, since this little picture here shows a anticipated development of a mathematical model of the left ventricle in 1974. So it was supposed to be finished by the end of my thesis, which was 1975, but we didn't quite make it. But I do think we're getting there slowly. And I think what is really important about the cardiac physiome project is that it's really being used as the template or the exemplar for a whole range of physiome projects. And there now are physiome projects across all of the organ systems of the body. But I think the cardiac physiome is definitely the most advanced, and people are looking to it as a guidance for doing multi-scale modelling, multi-physics, and clinical linkages. So I think it is extremely important that we think about particularly some of the infrastructure that's needed to sustain a physiome type project for the cardiac, because it will be applied to other organ systems. But I was rather surprised that, I mean, this does actually now include the brain, which is good, but I hadn't realised we'd made quite this much progress, because apparently, according to yesterday's Guardian, we're going to have a synthetic brain within 10 years. So if I'm optimistic, then some people are even more. So I think that probably the first important point to make is that we're rapidly moving to a situation where we are coupling all the physical processes at the organ level. I mean, we currently, in this meeting, have seen a number of coupled electromechanics, or several electromechanics models being developed by different groups. And we've also seen the beginnings of fluid structure interaction, coupling of ventricular flow and, of course, coronary flow to the myocardial mechanics. And I think it's quite reasonable to expect that in the next 3 years we'll take it as the norm that these models have all the physics of solid mechanics, fluid mechanics, and reaction diffusion processes properly coupled together, and that we then can take that as the norm, that we really begin to understand a lot of function and multi-scale function in particular, and clinical applications. Because all three processes are so integrated, and so any understanding of whole organ function has to be based on including all of those physical processes together. But equally, I think it's extremely important that we keep working on model reduction, keep thinking about how to make the models more efficient for the questions being asked, not just keep on piling in more detail, but really think carefully about how to achieve model reduction. And I think this is especially true for the activation work. I think when you look at the relatively smooth waveforms that are being produced by activation solutions, I think we're doing it the wrong way at the moment. We're paying a ridiculous price for something that should be a lot more efficient. And I think we need to think about the mathematics and think about the algorithms to be able to come up with much better ways of doing activation modeling. I think the mechanics is in a better state in terms of efficient solution of the equations. And the CFD, I'm not sure about it. It's just extremely hard to see how you could improve on to obtain more efficient computational techniques for the CFD part. But I think it's especially true for activation. I think, everyone would agree that we need to be including more complete anatomy. When we talk about a heart, we're really talking about a two-ventricle heart, not a four-chamber heart. And it's clear that we're getting close with the data that's being acquired and the computational methods that we have, that we could easily be fairly soon incorporating atria that are both electrically active and mechanically functioning. And the pericardium, we've had a go at doing this, but we've never really given it a serious, the contact problem associated with the pericardium. But it's pretty obvious that we really do need to be doing that. And I don't think it would add a large computational load to the mechanics models to be properly dealing with the sliding movement of the heart inside the pericardium. And likewise, we've seen work on the coupling of fluid mechanics with valves, but those are not yet properly coupled into realistic models of myocardial mechanics. And I think we need to be really pushing to do that in the next few years, because again, in terms of the coupling of the fluid mechanics, the valves are going to be crucial. And then, of course, likewise, the transfer of load from the valves through the chordae to the papillary muscles. It's pretty clear that the mechanical loading through the chordae are an important part of systole, and even the idea that the valves themselves are helping to actively control the outflow tract. Coronaries, I think, thanks to Nick and Jospan and their teams, I think we're in good shape with coronaries, and it's clearly going to get better and better as we understand more about how the coronary vasculature works particularly within the structure of the myocardium. So linking coronary structure to tissue structure. I see Purkinje fibers as a real problem, because there's such a huge variety of Purkinje fiber trees. Ian LeGrice in his thesis in Auckland actually did measure with Lugol staining Purkinjes for a number of dog hearts, and it's clear that there's huge variation. So we have to be able to figure out how to obtain the representative activation pattern for Purkinjes that doesn't need the detail, or at least has the statistics of the detail that you measure in individual hearts, but come up with ways of being able to properly distribute the activation to the myocardium through Purkinje networks that capture the key features of these complex Purkinje fibers. And then we have seen at this meeting some work on spatial distribution of ion channels, but I think we need to be doing a lot more of that. It's very clear we do have a good understanding of spatial variation of a number of channels. We really have to be making sure that the default models, the background models that we're using, just have this embedded properly in it. And I'll come shortly to the standards associated with making sure we have robust frameworks for doing that. And of course, more cell function. We have, it's great that we've currently got good models of ion channels linked to calcium transport, linked to myofilament mechanics, and great work from people like Jeff Saucerman, Andrew McCulloch and co. and Yoram Rudi's group on various signaling pathways. But we need to be doing a lot more of that and getting a lot more coupling of phosphorylation of the proteins involved in electromechanics properly controlled by the underlying signal transduction networks. And there's huge challenges here in terms of just the difficulty of getting the experimental data. But there's quite a few efforts going on, and I think we will see over the next few years significant increase in the number of cell models of signaling that are properly coupled, because this really is the key to the linkage from the cell bioengineering sort of view of the cell, dealing with mechanics, electrical function, calcium transport, metabolism, so on, but linking it down to gene regulation and the huge world of proteomics. So another thing I think that we're not doing nearly enough of is, and by we I mean not only everybody else, but the group in Auckland as well, should be doing more of this, which is to say we have this wonderful data coming from people like Ian LeGrice, Bruce Smales groups on understanding tissue structure and pulling out of that tissue structure detailed knowledge of, say, collagen density and orientation, sheet fiber structure, even gap junction distributions and so on, but we're not yet doing enough, I think, to build tissue models that capture that start with that structure, and out of that derive the orthotropic conductivity tensors or orthotropic material properties for mechanics that we can use in a constitutive law and the whole heart models. We're still a long way from getting a good link from a bioengineering view of a constitutive law to a proper basis in structure, because that's the only way that we're going to understand the way that heart failure, for example, influences those constitutive properties, because we can measure the change in organisation of or connectedness of sheets and collagen densities and so on. So unless we get that proper linkage from the microstructure through to the constitutive laws, we're not going to be able to understand these disease processes. And I think part of that process has to be to do with growth modelling. I mean, Peter Bovendert has made a start there, and I think it's extremely important that we get good models of tissue growth. The background theory is fairly well established, thanks to people like J. Humphrey and mixture theory. So we should be using that with this detailed data that we have to be able to link into the constitutive properties. And then there's a question of, should we be building this type of structural information into the models in a dynamic sense? In other words, making our codes much more sophisticated in the sense that as you proceed with a solution, you bring in the multi-scale new data appropriately to deal with the particular issues that are arising during the solution process. So I think we should be getting a lot smarter with code that allows us to move up and down scales and bring in the necessary detail at the right point, not making ridiculously complicated models, but just bringing it in at the right point to answer the questions as the model proceeds. That's a big challenge, but I think it is an achievable one. Then my fourth point on this list is clinical applications, because there's no question that the funding for this area is going to be dependent on our ability to generate clinical outcomes. And Reza Razavi gave a very nice, eloquent plea for how clinical applications need the modelling infrastructure to improve outcomes, particularly for, in his case, for cardiac, but across, of course, all applications of models in medicine. But I think these are starting to come. The programs like the UHeart project are really beginning to, with their focus on linkage with the companies like Philips and others, Berlin Heart in this case, are beginning to really drive some of the models closer to clinical outcome. And that's so important for long-term funding, that the belief that the modelling efforts are going to result in useful outcomes for society, quite apart from the knowledge of how things work, that they can actually be used clinically. And that requires a lot of thought about clinical interfaces, as Nick illustrated and for the UHeart project. And we just have to get these models to the point where they're used in clinical trials. And it would be fantastic if we could reach that point in the next 3 or 4 years as part of the UHeart project. I think the models, and it's very clear, many people think this also, that they've got to be able to be personalised in many cases, not always, but in many cases the process of figuring out how you use clinical data, how you adapt partly from a population database, as Alistair talked about with the CAP project, how you can use a combination of population data with patient-specific or person-specific measurements to be able to inform a clinical outcome with, or a clinical therapy, for example, or the design of a device or choice of a device, based on that combination of population information that will often come partly from looking at lots of human hearts, but also bringing in the whole wealth of animal work through the models to bear on the clinical problem. And I think what we have to be also striving to do is to make it more multi-scale, so that we are dealing not only with the problems of applying these models at the clinical level from the point of view of whole organ physics, but also linking down to what we can measure in the blood, for example, of a patient, that can inform this process for that patient by using the multi-scale modelling framework as well. So all of this, I think, is crucially dependent on the development of standards. I mean, it's, for most people in the modelling world, these are boring topics that you just want to be able to get on with doing the modelling. But unless we develop the robust standards, we're simply not going to have a decent framework for applying all of this to clinical outcomes. We've made a good start, I think. Paul this morning talked about the CellML developments. There's a comparable effort going on at EBI in Cambridge with SBML for the systems biology, and there's now a program dealing with spatial information, FieldML, which has got input from a number of groups, and these groups are working together. We had a meeting in Auckland in April, and there's, I think, real progress in terms of developing common metadata standards between the CellML and SBML communities and good interchange between the two markup languages. And then we need to be moving to a situation where the APIs based on these can be incorporated into code so that you can directly load the particular choice of models from these databases directly into the tissue organ level codes. And the model databases, I think, are also coming on quite well. There's both the CellML and SBML databases each have around 400 models, about half of them curated. So there's good progress, a lot of effort going in to try and provide these models publicly in a curated form via these standards. But there's still an awful lot more to do. We need to be having, particularly around data standards, we really need to be creating standards that allow us to encode the data as well as the models in a robust way that people can then check how robust the models are against experimental measurements, check predictions against measurements on a much more robust and automated fashion, particularly for reproducibility. If other people can't reproduce results through these public domain databases, then how do you believe the results? So it really does, it is extremely important as these models get very complex that we've got good mechanisms for demonstrating reproducibility, let alone validity, of course, through all validation processes against experimental data. And as Jim Basingthwaite this morning mentioned, there's also his JSON and model database as well. I think we should be moving much more to collaborative code development. I think there's too many parallel efforts that are just reinventing the wheel, and we have to figure out how to do this better, to give people proper credit, but to develop open source codes that are for the community, that are shared and have effort going in from a number of groups around the world, because these are big challenges and we should be working collaboratively at the code level to solve these challenges. And some of that is beginning to happen, partly stimulated by some of the European Framework 7 efforts. So a lot of the development of standards are being led by partly the IUPS physiome project, but also now the virtual physiological human. And what's really great, I think, is that the European Union is very keen to promote, despite these being European projects for the VPH, they're very keen to promote international collaborations, work with NIH to have joint funding of common programs between Europe and the US and the rest of the world. And so we adopted the symbol for the VPH to be identical to the symbol for the IUPS Physiome project deliberately to indicate that we're really talking about the same project. This is the European contribution to it, and it has a very strong clinical focus, but it is working very closely with the efforts going on for the International Union of Physiological Sciences project. And in fact, next week, a number of us are going to the World Congress, which is held every 4 years, and this year it's in Kyoto in Japan, where there'll be a number of symposia on the Physiome project and workshops running with the tools, showing people about the markup languages and so on. But it's now just taken for granted that when we talk about Physiome, we're talking about the combination of VPH and Physiome, because these two projects are really well integrated. And as I said before, I think the big challenge for us now is data standards. We've got to get a lot better at figuring out how to encode data robustly to use with the models. So just a few other quick thoughts. I think we're not doing nearly enough with error analysis, parameter sensitivity. confidence limits in our models. And we had the talk by Simon Taverner, who I think is indicating a path that we could be following to be able to solve both the primal and the dual problems in order to get more information on error analysis and parameter sensitivity. But this is going to be very, very important, of course, for the clinical applications of these models, that we have some real confidence about how they can be applied, or have some indication of what level of confidence we have. Another of my big challenges, or challenges I see for the physiome project, is closing the gap between bioengineering and systems biology. At the moment, there's a very, very tentative link between these two things. If you think of systems biology in the rather narrow sense of networks, gene regulation, metabolic pathways, signaling, etc., that this community currently thinks about, and the development of frameworks using high data throughput technologies feeding into network models, I mean, the sort of world that Lee Hood has so eloquently promoted, then I think we're very disconnected from the community that's doing the more bioengineering, biophysics-based modelling. So we've just got to get better and better, and I think the standards will help a lot with this in connecting these two things together. And as Stieg this morning showed, I think one of the challenges is ageing, growth, development, ageing, which is going to depend very much on this linkage, because so many of these processes involve change gene regulation, gene expression. And as Stig also mentioned, the need to be linking genotype to phenotype maps through these biophysical quantitative models, and he's talked a lot about that this morning. So finally, I think the 10th point is that we should have another meeting. This is the third, or really the fourth in the series. The first one was really the meeting we held in Queenstown in New Zealand in 2001. That was the first big cardiac modelling focused meeting associated with the cardiac physiome. And then the second one was in Oxford, the third one New Zealand, and this is really the fourth. And we certainly want to keep this tradition going. I think we owe a huge debt of gratitude to Nick. I mean, there were 4 people on this organising committee. I did by far the least, and both Richard and Sarah also feel that the weight was carried very much by Nick, who not only has a baby on the way, but is also leading the scientific program in the UHeart project. So he's got a huge amount on his plate, and to have pulled this meeting off, to have raised the money, to organise it on top of all of that, I think we really deserve we'll give him a good round of applause. I was going to give him a box of chocolates, but he's such a athletic freak that he wouldn't eat them, so we've had to make do with a virtual one. So.
Peter, questions?
Well, it may not be as
Peter, there is a cardiovascular research grid at Hopkins. I'm not part of it, but I'm aware of it. And they have it's more of a data repository for imaging data and other, not just electrophysiology, but anything cardiac.
Yeah.
Is there any effort to link that to the physiome or?
Yeah, funny you should mention that, because Alistair was talking to me this morning about
Oh, is that right? Okay.
I think Alistair, as part of his CAP project, is linked into the Hopkins database of 5,000 patients, and is linked with Ray through, and has had a lot of discussions with Ray about that. But I think and Alistair's also now thinking about an NIH application that could provide more grid enablement of tools that would then make use of the infrastructure that Ray Winslow is developing.
Yeah, because this is, we are lacking this sort of a wealth of data, us as modelers, that is out there somewhere contained in various centers, and it would be great to have a repository that we can access.
That's right. So as well as the data standards, I mean, for clinical image data, of course, DICOM is now by far the dominant standard. But we don't have standards around a lot of other forms of data. And often it's not the issue of encoding the data itself, which you can use HDF5 and some of those high-density formats. It's more the metadata and the structures for how you deal with the annotation of the metadata. And I think also linking to SNOMED CT and some of the clinical, the big clinical databases that are used through ontologies used in hospitals. Like it or not, ontologies are a vital part of this whole effort. So I think the VPH, the NOE, Network of Excellence for the VPH, is really pushing this clinical link with standards, partly facilitated by the work that EBI in Cambridge has done. I mean, for years they've been developing infrastructure for handling ontologies, very keen to push that closer to the clinical, and they've built big databases, of course. So we're working closely in the NOE with EBI in Cambridge and working with people like the Seattle group, Cornelius Ross, and the group in University of Washington, Seattle, who've developed some of the ontologies for anatomy. And I think I see over the next few years that we will really start to pull together common terminology, access to better data to link with the models. I hope so.
I'm still astonished how little the impact of this activity in the large cardiology societies actually is. I'm in the European Society for Cardiology and dealing with the basic science community there, and it's very little what you hear about the cardiac physiome over there. So I think it would be needed to bring these two efforts together more closely and maybe find a way of having a joint meeting, because that's where you are heading to. And if you want to bring it into the clinic, you need them to really exploit the possibilities of a cardiac physiome and the modeling on this level for their questions, like in electrophysiology and so on and so forth. And when you go around there, and I see this basic science program for the last 10 years, there's nearly nothing with close relation to what's going on here.
I mean, it's the same. If you go to experimental biology in the US, where you have 20,000 people who are doing experimental biology, there's probably 100, maybe 200 there who are doing modeling. So there's a huge imbalance still, although we have, in some of these meetings now, we've got a physiome track in experimental biology, which Dan Beard and Alan Cowley have been helping with. So but we need to be doing that with a number of these more clinical meetings to get essentially sessions organised that people who have an interest in the modelling side could come to as part of those meetings, I agree.
Just to follow on the same subject, I think one piece which seems to be missing in the whole concept of physiome is the following. So you aim to describe and perhaps predict physiology, normal or path physiology, but what is missing is what exactly it means to have certain clinical or basic science intervention or measurement done in your construct. So for instance, what is the physics behind radio frequency ablation and what it would translate into a signal which will be sensed clinically or in a basic lab?
Yeah.
Because right now you're showing very nice pictures, but how do they directly relate them to what cardiologists can see or basic electrophysiologists with optical mapping can see? So this is really missing.
There is some of that in the imaging work. I mean, we've heard talks in this meeting where people are talking about some of the models that are available for understanding the physics of imaging devices. So the process of interpreting the images can make use of these quantitative models of how your image relates to what you're seeing, what the original data was. But I agree. I mean, I think we need good interaction with medical physicists for making sure that the models applied to clinical data are taking account